Okay, so we're going to continue talking about gases today, and let's talk about the Dalton's Law. So Dalton's Law of partial pressures. Partial pressures. Okay, so it says that P total is equal to the pressure of gas number 1 plus the pressure of gas number 2 plus the pressure of gas number 3, right? If you've got a mixture of gases inside a vessel, or like we're breathing right now, right, total atmospheric pressure is equal to the pressure of gas number 1 plus the pressure of gas number 2 plus the pressure of gas number 3, et cetera, et cetera, et cetera. Okay, easy enough. Now up to the side here, who remembers the ideal gas law from Monday? PV equals nRT. If we rearrange this for pressure, how will we get pressure by itself?
Divided by V.
Right. P would just be nRT over V, right? So if we substitute that, nRT over V plus nRT over V plus nRT over V for number 1. You don't have to write this down, just watch. I'm just deriving it for you. All right, R and T are going to be a constant, right, at a given temperature. So you can factor that out. P total is equal to RT over V times N total, right? Because the volume of the container is going to be a constant. If all of these are in a 5-liter container, well, that's going to be a constant in all 3 of these. R is the gas constant, so that's constant all the time. And if we're in the same flask, obviously the temperature is going to be uniform throughout the flask. So P total is equal to RT over V times N total. That's a formula worth knowing, right? This part and this part. I wouldn't make you derive it, but it's nice to know where it comes from, right? It's nice to know where these formulas come from. If this is all taking place in a sealed container, volume's constant, temperature's constant, R is definitely constant. So if we factor that out, you add up number of moles, number of moles, number of moles, and multiply by that constant, that'll give you the total pressure. Now, obviously, if we don't have enough information to do it this way, like for instance, if we don't know the volume of the container, or we don't know the temperature, we could just do it this way, right? So for instance, the air we're breathing right now, obviously we would do this way. Does everyone understand how to do this? Now, I know that there is a question on the homework dealing with Dalton's Law, probably a couple of questions dealing with Dalton's Law for mixtures of gases. So I want to go over an example and then give one for you to try. All right, so let's just start with a fresh marker. When my kids come to my office, they mix up all my markers. I don't know which ones are good or old anymore. Okay, so let's do an example. Let's see. Well, let's make that pressure a little bit lower. You have a 10-liter tank containing gas number 1, we'll just call it gas number 1, at 23 degrees Celsius and 1.95 ATM. Gas number 2 is at, let's say, 1.74 ATM and 27 degrees Celsius, and its volume is 9.0 liters. You fill a 7.5 liter tank from these 2 tanks at 25 degrees Celsius. What's the pressure? Okay, so there's a lot of information thrown at you there. I'm going to give you a second to copy that down before I start going over how to do it. Okay, let's go over how to do this one. So we've got a lot of information. We've got 2 tanks. We're going to mix them together and pump that into a 3rd tank. So if you want to make yourself a little sketch, that might help. So let's draw tank number 1. This is tank 1. It is 10 liters. It is 23 degrees Celsius. It is 1.95 ATM. Here's tank 2, slightly smaller. It is, what's its volume? 9 liters. It is 1.74 ATM, and it is 27 degrees Celsius. So we're going to mix them. So let's just draw ourselves a little schematic here. We're going to pump them into tank number 3, which is 7.5 liters, and it is at 25 degrees Celsius, and we want to know what the pressure. Okay, so P total is equal to RT over V times N total. Well, we have R, because that's a constant. We have T and V. How do we get N total? Where's that going to come from? How can we get number of moles? Do we have everything we need to calculate number of moles here and here? Yes, we do, right? What formula would we use? Not polarity, because we don't have any way to get mass. We could use the ideal gas law, though, couldn't we? PV equals nRT, right? So if we do PV equals nRT and solve for N here, we do PV equals nRT and solve for N here, that gives me N, that gives me N. I add those together, that gives me N total. Does everyone see how we do this? So now we just have to do ideal gas law times 2. I'm going to say it inside a frame here. Okay, we got room. So let's do tank 1. I know I'm kind of squished here, but I'm trying to stay in the frame. PV equals nRT is the ideal gas law, right? That's the most important gas law. To get N by itself, how would that be? That would just be N is equal to PV over RT, right? So now let's just plug in our information. I'm going to run out of room. Just erase the equation. So pressure is 1.95 atmospheres. Volume is 10.0 liters. R is 0.08206 liter atmosphere per mole Kelvin. And temperature is 23 degrees Celsius. What's that in Kelvin? So we can't use Celsius. 296. And for those of you watching at home, let's remind ourselves, how do we convert Celsius to Kelvin? We just add 273, right? So atmospheres cancels, liters cancels, Kelvin cancels, 1 over moles gives me units of moles, right? So now we find our calculator. 1.95 times 10 is just 19.5. And then 0.08206 times 296, 24.29. So 19.5 divided by 24.29 gives me 0.803 moles. We'll do our rounding at the end. So that was for tank number 1. And then for tank number 2, it's still N is equal to PV over RT, right? Because PV equals nRT, so N is just PV So N is just PV over RT. So now let's plug in our information. Pressure is 1.74 atmospheres. And volume is 9 liters. Divided by R, still 0.08206 liter atmospheres per mole Kelvin. And then what's my temperature here? For 27?
Oh, sorry. 300.
All right, so 1.74 times 9, 15.66. My denominator is 0.08206 times 300, 24.62. So 15.66 divided by 24.62 gives me 0.636 moles. So now I'm able to solve for my final answer, right? Because those are the number of moles in my 2 original tanks. I mix them all together and pump that mixture into here. So P total is RT over V. That's RT over V times N total. So 0.08206 liter atmosphere per mole Kelvin. Temperature here is 298. And the volume, 7.5 liters. And what is N total? Just add those two together, right? So plus 0.803 times 1.439 moles. So moles cancels, kelvins cancels, liters cancels. That gives me units of atmospheres as my answer, which is what I wanted. So times 298 times 0.08206 divided by 7.5. I got 4.69. I erased my problem. How many sig figs could I keep? I think I can only keep 2, right? 4.7. That's pretty high pressure, right? That's 4 times, almost 5 times what we're feeling right now. Do we see how to do these kinds of problems? It looks scary at first because you're like, I got all these numbers. But if you just split it up, look at what the problem's really asking for, it's really not that bad. So I'm going to give you one to try. That one does a thorough job. Okay. A 5.0 liter tank of argon has a temp of 31 degrees Celsius and 1.11 atm pressure. A 7.5 liter tank of helium has a temp of 33 degrees Celsius and 0.96 atmospheres pressure. You mix into a 20 liter tank at 35 degrees Celsius. What is the pressure? So I'll pause the recording and let's try that one. All right, let's go over this one. You might not be finished yet, but that's okay. So let's list out all of our information. You don't have to draw yourself a schematic if you don't want. You can just list your information. So tank 1, tank 2, and then the mixture. Tank 1 is 5.0 liters. It is 31 degrees Celsius and 1.11 atmospheres pressure. Tank 2 is 7.5 liters. It is 33 degrees Celsius and it is 0.96 atmospheres. And then the mixture is 20 liters, so we're filling up a big tank, and 35 degrees Celsius. So we'd have to actually add something to that to get it up to 20. So let's just pretend we add some sort of inert gas to get it up, because 5 plus 7.5 doesn't equal 20. So let's pretend we add some sort of filler to get it up to 20. Okay, so we've got to do PV equals nRT twice, right? If PV is equal to nRT, then N is just PV over RT, right? You could plug directly in and then do your arithmetic like you did in algebra class in high school. It's the same exact thing. So let's just go through and solve for N. N1 would be P, so 1.11 ATM, and then V, 5.0 liters, 0.08206 liter atmosphere per mole Kelvin. And then what's my, that's a parenthesis. What's my temperature? Can I plug in this 31? What is that in Kelvin? 304 Kelvin. So, calculator, let's see. Atmospheres cancels, liters cancels, Kelvins cancel. So I know that my answer is correct, or at least set up correctly, because I'm going to have units of moles, right? 1 over moles would give me moles. So 1.11 times 5 divided by 0.08206 times 304. I got 0.222 moles. And then here, N2 is pressure 0.96 times my volume is 7.5 liters, 0.08206 liter atmospheres per mole Kelvin. And then what's this temperature in Kelvin?
306 Kelvin.
306. Okay. Again, liters cancels. Oops, I forgot my atmospheres. Atmospheres cancels. Kelvins cancel. I like to put my units in just kind of as a self-check, right? Because if all the units go away that you don't want, then you know you've got it set up at least correctly. 0.96 times 7.5 divided by 0.08206 times 306. I got 0.287 moles. Did you? All right. So now P total is equal to RT over V times N total. So R, 0.8206 liter atmospheres per mole Kelvin. Temperature, what's this in Kelvin?
308.
308 Kelvin. And then N total is just those two together. So 0.222 plus 0.287 gives me 0.509. Divided by the volume, which is 20. Okay, liters cancels, Kelvins cancels, moles cancels. All right, so times 308 times 0.08206 divided by 20. I got 0.64 atmospheres. Do we agree? Yes. Again, you'd have to add some sort of inert gas to make it up to 20. But of course, you could just let it expand. That would work too. All right, so let's move on if we're okay with this kind of problem. I'm pretty sure there's one like this on the homework, so I want to make sure we get through at least one where you practice it in class. Let's go on to a second kind of problem that we can do with gases. All right, so let's talk about the density of a gas, because gases are unique. They're not like liquids, right? The density of a liquid is pretty well constant, right? It's very difficult to make the density of a liquid change. It's very difficult to make the density of a solid change. It's virtually unchangeable. Gases, on the other hand, are variable, right? They can expand, they can contract. So gas density, what is the formula for density?
Mass over volume.
Right, it's just mass over volume. Is there a way that we could get mass from, say, the ideal gas law, and then, oh, I don't know, plug it in here? Yes, it'd be really easy, right? So all you need to do here to get gas density is use PV equals nRT, solve for N, convert to grams, and then plug her in. Right? That's all you need to do when we're dealing with a gas. The gas's temperature will play a big role in its density, and the gas's volume will play a big role in its density, right? You can let a gas expand, you can compress a gas down. That's one of the unique things about gases, right? You can't do that with liquids. If you've got a liquid, you're trying to compress it, good luck, right? You're not going to be able to get very far with that. You're trying to compress a solid, double good luck. But with a gas, you can compress it because the gas is just empty space. There's a lot of empty space, you can just smush it together. All right, so let's do a gas density problem. Does everyone understand the procedure? Right, it's a pretty straightforward procedure. If you understand the ideal gas law, then you can solve for these things. How is the density of 5.5 liters of argon in 25 degrees Celsius and 0.99 atmospheres different when the volume is changed to 15 liters. So what would you expect to this density when you go from 5.5 liters to 15 liters? What would you expect to happen to the density?
Drops.
You'd expect it to go way down, right? Let's see if we can confirm that. So let's do argon gas at 5.5 liters, argon gas at 15 liters. So let's do first scenario. PV equals nRT, right? So what are we solving for? Remember, we have to solve for something before we can plug it into the density equation. You have to solve for N, right? So N is just PV over RT. So let's see, the pressure is 0.99. And the volume is 5.5 liters. And R, 0.08206 liter atmospheres per mole Kelvin. And then the temperature, 25 degrees Celsius, what's that in Kelvin? 298 Kelvin. So atmospheres goes away, and liters goes away, and Kelvin goes away. So let's see, 0.99 times 5.5 divided by 0.08206 times 298. I got 0.223 moles. Now this is the 5.5 liters. All right, let's do it at 15 liters. And it's still PV over RT. So then everything stays the same except that volume, 0.99 atmospheres, 15 liters, same denominator exactly, 0.08206 liter atmospheres per mole Kelvin. Still 298 Kelvin. So 0.99 times 15 divided by 0.08206 times 298 gives me 0.607 moles. All right, so now we just need to convert to grams, right? Because density is mass over volume. So what's the molar mass of argon? We just have to look at our periodic table. I can't see that far. 39.9, I think, is what it is, right? 39.9 grams per mole. 39.9 grams per mole. So times 39.9. So that's 24.22 grams. And then 0.223 times 39.9 is 8.897. Okay, so that means I'm going to run out of frame. The density of the 5.5 liters is mass over volume, so that's 8.898 grams divided by the volume was 5.5. And then the density at 15 liters, still mass over volume. So that's the 24.22 grams divided by 15 liters. All right, so divided by 5.5, 1.6, I can't remember how many sig figs. Let's see, I think it's 2, right? Yeah. 1.6 grams per liter versus 24.22 divided by 15. It's actually within sig figs, 1.6 grams per liter as well. So if we carried out more sig figs, we would have been able to see the difference, right? So it's actually not an appreciable difference if you only have 2 sig figs. So it's a nice measure of sig figs there too. If we carried out more significant figures, though, we would have seen a difference. All right, you guys ready to try one? Just for good measure, make sure you know how to do this. I'm almost certain there's one like this on the homework as well, so we want to make sure we have the opportunity to practice it. All right. I won't make you do a before and after one. We'll just do one of them. Because if you can do one, you can do 1,000 of them. As long as the procedures, what you know how to do, you can plug in any number you want. Let's see. You have a 20, more sig figs time, tank of chlorine gas at 30.0 degrees Celsius and 0.873 atmospheres pressure. What is the density? I'll pause the recording and let you try this one. Okay, we've got a 20-liter tank, and it's containing chlorine gas at 30 degrees Celsius, and the pressure is 0.873 atmospheres. What is the density? So eventually we need to be able to plug into density is equal to mass over volume. We don't have any way of getting that right now, though, right? We have to do some preliminary calculations first. So what do we need to solve for first? number of moles, right? So we're going to use PV equals nRT. So that means that N is just PV over RT. So the pressure is 20 liters. And the, oh, that wasn't the pressure, that was the volume. The pressure was 0.873. Nice thing about multiplication is order doesn't matter. 0.08206 liter atmospheres per mole Kelvin. And then the temperature, what's this temperature in Kelvin? 303. Okay, liters goes away, atmospheres goes away, Kelvin goes away. So this gives me 20 times 0.873 divided by 0.08206 times 303. So I got 0.7022 moles. Do we agree?
Yes.
Now, do I just multiply that by 35.45 and I'm off to the races? No, why not?
Chlorine gas is a diatomic.
All right, chlorine as a gas is diatomic, so it's not Cl, it's Cl2. So 35.45 would be incorrect, right? So we want to use 71 grams per mole.
That's really close.
All right, so times 71. So that's 49.86 grams. This moles cancels. Now we can plug into our density equation. Did that go out of the spring? Oh, no, just barely. Okay, so density is equal to mass over volume. So 49.86 grams. Volume is 20. So divide my answer by 20. You get 2.4. How many sig figs can I keep? 3. 2.49 grams per liter. How do we feel about that? Easy, easy, easy. Okay, let's talk about how we can use this same principle to solve for molar mass, because we can actually solve for molar mass as well. Here we're using molar mass as part of the density equation, but we can actually solve for molar mass from some density calculations. So let's talk about how we do that. I remember when I was in high school, we were doing a lab like this, where we were solving for the density. I mean, we were solving for the molar mass of the gas, and I somehow got a negative number. So our gas had a negative molar mass. I don't think that was right. What do you think?
You made up it's like antimatter.
Yes, I'm waiting for my Nobel Prize. Okay, so I'm not going to derive the equation for you. It's an easy derivation, but we're kind of running low on time. And I've got one more thing I want to show you. So again, just a reminder, just FYI, on the exam, I will give you a reference page with these formulas that we've derived. Okay, so the only one you're responsible for knowing is PV equals nRT. Okay, and if you can remember that one, I'll give you the derivations of it on your reference page. Sound fair enough?
Derived from the derivation.
Yes. Molar mass is equal to dRT over P. That's a D. Where D stands for density. And then R and T and P are the same as in the ideal gas law. Okay, that's molar mass. So let's do an example. Is everyone okay if I erase that? You got it jotted down? Because I want to use the whole space. You do an experiment to ID a gas. Because remember, every gas has, a unique molar mass. Obviously, if we start getting into compounds, there are a lot of compounds that have the same molar mass, so you'd have to do more than just molar mass to identify a gas, but let's just use that as a starting point. The following are your data. All right, so let's just list it out. Let's pretend that you're at a temperature. Let's just pretend you're doing this at room temperature. and a volume of 8.5 liters and a pressure, let's pretend we're at 1.54 atmospheres. And we want to know what's the molar mass. Now obviously there are going to be multiple compounds that would have the same molar mass, but we can at least use this as a starting point, right? Get in the general ballpark. So first thing we need, if molar mass is dRT over P, what do we need first? We need to find the density, right? So how do we get density? What do we have to do before we can get density? We have to find number of moles. So I guess we'd have to figure out, let's see if we have to have the number of moles. So let me just tell you that the density experimentally is 4.33 grams per liter. Because obviously you couldn't solve for density without molar mass, right? That'd be kind of a problem. So there's the density. Let's just pretend our experimental density was determined to be 4.33 grams per liter. Could we solve for it now? Yeah, we could. All right, so let's see. Molar mass is dRT over P, so 4.33 grams per liter times 0.08206 liter atmospheres per mole Kelvin, and then temperature is 298 Kelvin, all divided by the volume, which is 8.5 liters. All right, so those liters go away, and let's see, grams, moles, that's grams per mole, so that's what we want, and then Kelvin, and oh, it's dRT over P.
Yeah.
Like, why is my atmospheres not going away? There we go. Atmospheres is 1.54. See, that's why it's nice to plug in your units. Self-correct silly little mistakes. So now we're left with grams per mole, which is the units of molar mass. All right, so 4.33 times 0.08206 times 298 divided by 1.54. So the experimental molar mass of this would be 68 point, how many sig figs are we doing? 2. 68.75, so 69 grams per mole. All right, I've got a problem that I just made this up off the top of my head. I've got a couple that I actually have worked out from real experimental data. I'm going to pause the recording while I fish this out of the computer here. Pause. Okay, so here's some actual data. I'm going to throw these up on the screen, or on the board here, and I want you to solve it. I'll see if you can figure it out. I'll pause the recording once I've got it all up here. All right, so where'd my data go? Hold on, I just lost it. Okay, so you are doing a lab to determine molar mass of krypton. Okay, so you're trying to determine the molar mass of krypton. You know what krypton's actual molar mass is, right? So see if you can figure out, based on this student's data, was this a good day in the lab or a bad day in the lab? So here are the data. Let's see, pressure is 4.6 atmospheres. And temperature, 20 degrees Celsius. And the volume of your container was 0.92 liters. So you decide, did this person have a good day in the lab or a bad day in the lab? I'll pause it and see if you can figure this one out, and then we'll go over it. I know that everybody might be finished yet, but let's go over this one. So molar mass is what? What's the formula? Let's list our formulas. Molar mass is
Density
dRT over P. But before we can do this, we have to get density, right? Density is what? Mass over volume. And before we can get density, we have to solve for number of moles. So N is equal to PV over RT. So this is a three-step problem, right? Here, convert that to grams. Here, convert that. You don't have to do any conversions here. Then just plug it in and go. So let's do our first calculation. N is equal to PV over RT. So 4.6 atmospheres times 0.92 liters divided by R, 0.08206 liter atmospheres per mole Kelvin. And then temperature is 20 degrees Celsius. So what is that in Kelvin?
393.
What?
393.
393?
Oh,
That seems high.
293.
Yeah, I was going to say. 293. Okay, so atmospheres cancels, liters cancel, Kelvin cancel. So 4.6 times 0.92 divided by 0.08206 times 293. So I got 0.176 moles. Now let's turn that into a density. So 0.176 moles. Now we're using the fact that we know that this is krypton, right? Because otherwise we'd be stuck. But we're trying to figure out, using our data, to come up with the experimental molar mass of krypton. So the molar mass of krypton is what? 83.798. Grams per mole. So times 83.798. That gives me 14.75 grams. That means my density is 14.75 grams divided by my volume, 0.92 liters, divided by 0.92. That gives me 16.03 grams per liter. So we did that, Now we're ready for molar mass. Final step. Molar mass is equal to dRT over P. So my density is 16.03 grams per liter times R, 0.08206 liter atmospheres per mole Kelvin. And my Kelvin temperature is 293. All divided by my pressure, which was 4.6 atmospheres. So atmospheres cancel, Kelvin cancel, and liters cancel. So that gives me grams per mole as my units, which is what I want. So times 0.08206 times 293 divided by 4.6. Oops. I typed in the wrong number. 16.03 times 0.08206 times 293 divided by 4.6. I typed 1.6. 83 point, how many sig figs? 2. Well, let's just keep 3 for decimal places purposes. 83.8. Actual molar mass is 83.79. So yeah, that was a good day in the lab, wasn't it?
Very little error.
All right, happy face. Okay, that's where we will stop for today. We'll have one more little problem we'll have to go over, and that is the issue of stoichiometry. We'll deal with that on Friday. And we'll deal with collecting a gas over water on Friday. So otherwise, I'll see you then.